Box and whisker plots are a useful way of presenting statistical summary data. However, without an understanding of the concepts of outliers and interquartile range, box and whisker displays will make very little sense in terms of interpretation. For this particular lecture to make any sense at all, you'll need to have a firm understanding of the concept of the median and its application. If you haven't watched the prior video within the Introduction to Statistics playlist, I would suggest that you might consider doing so. Also in this video, we will discuss the concept of outliers in depth and when their removal is appropriate. So we'll begin with the definition of outliers. In statistics, an outlier is a data point that differs significantly from other observations. An outlier may be due to variability in the measurements, or it may indicate an experimental error. The latter are sometimes excluded from the dataset. An outlier can cause serious problems in statistical analysis. So when is it appropriate to remove outliers? It's appropriate to remove outliers when the values in the dataset would otherwise skew results or distort the overall analysis. When is it not appropriate to remove outliers? In most situations, with the exception being the scenario previously described. So in a more, I suppose, layman explanation or pragmatic application, as it were, if you had a situation in which you wanted to fully and robustly and completely summarize data, you would leave the outliers within your data set because that would be the fullest and most robust summary of the data available to an outside observer. However, if there was a situation in which you believe that the outliers within your data set, and typically this can be the case when the data set is smaller as far as the number of observations are concerned. If you believe that those observations within your smaller data set are really having an impact as it pertains to an outside observer looking at your findings and summarizing them, then you would want those outliers removed. So for an example, if you were, say, had a class of 30 students and you wanted to gauge appropriately the average height of the students within the classroom, well, you could do the mean value, the average, and you could present that to maybe your department head for whatever the purpose may be, so they could determine what the average weight or height of those students is. However, if there's certain circumstances where in your class you have maybe one or two individuals who were let into the university just to play on the basketball team and they're 6'8" or 6'9", well, that might cause a skew. So you would be operating then under the pretense that the mean of the students within the classroom is a certain height, but that height, that mean would be brought up just by having those two or three individuals on the basketball team within the class. So it wouldn't be a full or maybe accurate explanation or accurate summary of the student height that you would traditionally expect in your classroom from semester to semester. So in that case, you might want to consider removing the outliers. So here's the typical method utilized to discern outlier values within a observational series. Outliers are typically defined as values that fall 1.5 times the interquartile range below the first quartile and 1.5 times the interquartile range above the third quartile. So of course, with this, we need to explain what the interquartile range is and what quartiles are if you are to understand how to perform this analysis. And I should mention, there are different ways to define outliers, different methodologies that can be utilized. This is one of the most common. If you're doing research, you want to write in your method section what technique you utilized as it relates to outliers and the definition of such, what methodology was employed. And you also want to record how many outliers you removed from your data set if you did go about removing outliers and what the range was. You just don't want to haphazardly remove individuals from the data set and then present those findings to a reader. So in descriptive statistics, the interquartile range, which is commonly abbreviated as IQR, also called the mid-spread, the middle 50%, or the H-spread. No one actually calls it those. They always refer to it as the interquartile range or IQR. But if you do encounter mid-spread, middle 50%, or H-spread, they're referring to interquartile range. In any event, the interquartile range is a measure of statistical dispersion being equal to the difference between the 75th and 25th percentiles, or between the upper and lower quartiles. So interquartile range equals the third quartile minus the first quartile. So here's an example from Wikipedia. So in this instance, we have 13 observations within our data set. And the X values there are the observational values. So 7, 7, 31, 47, 75. These are our observations. And this is the position, the element position of the observations within our data sets. This was our first observation, second observation, and so on and so forth. So the median of this data set is 87. Now, why is it the median? Well, if you are familiar with median as a concept, or if you watched the video, which I recommended in the second slide of this presentation, the median is, in this case, the seventh observation because we have an odd number of observations. So 1, 2, 3, 4, 5, 6, 7, median, 87, 8, 9, 10, 11, 12, 13. So we count 1, 2, 3, 4, 5, 6, median, 1, 2, 3, 4, 5, 6. It's the odd middle, or median for that matter, observation. So median is 87. Now the median of the upper half from row 1 to 6 is 31. So 1, 2, 3, 4, 5, 6. So what's the median here? Well, we have a tie with our two values because it's an even number of observations. So 7, 7. Here's our middle two values. 31, 31, 47, 75. So in this case, our median is 31 plus 31 divided by 2, which is 31. Okay, 31, 31 summed divided by 2 is 31. And down here, our median of the lower half from 8 to 13, well, we have 1, 2, 3, 4, 5, 6. So in that case, our median values of this subset here are the sum of observations 10 and 11, which are 119 and 119. Add those together, 119 plus 119 divided by 2. That's the median value of the subset, which is also the third quartile, so that's 119. All right, so our first quartile is 31, which is the median of this subset, and our third quartile is 119, which is the median of this subset. So the interquartile range is then the third quartile, 119, with the value of the first quartile, 31, subtracted from it, which gives us 88. So the interquartile range is 88. So here are some examples if you wanted to visualize this process in Excel, or just, through this illustration that I have here, which was created from a combination of Excel and my Microsoft Paint mastery. But in any event, what we have here is we have data which is sorted in ascending order, so lowest values to highest values, lowest values to highest values, all right? And we have our first quartile, okay? Here's the median, and here's our third quartile in this case, and we have to find the median of these subsets. So 31 is the median here. 119 is the median here. So the value of our first quartile is 31. Median of our third quartile is 119. And then the difference is our interquartile range. That's what we did in the prior slide. And in this instance, we have an even number of observations, okay? So we have an even number of observations. So in this case, we have two equal sets. We're breaking our data perfectly into two subsets. In this case, we had the median that we had to work around. In this case, we have two perfect subsets because it's a number even observations. And so what we're going to do is here, the median for set 2, our first quartile, we count 1, 2, 3, 4, 5, 6, 7. So our median value is 31 because this subset has an odd number of observations. So 1, 2, 3, median value, which is 4, 5, 6, 7, or 1, 2, 3, median value, 5, 6, 7. And the same is true for this subset here. 1, 2, 3, median value is 118, 4, 5, 6, 7. So our first quartile value is 31, and our third quartile value is 118. We subtract 31 from 118, and we get the interquartile range for this observational set, and that's 87. So if you wanted to solve this in Excel, here's how you would do it. You first have to enter all your data into an Excel workbook. All right, so this is one of the sheets in an Excel workbook. You then want to be sure that your data is sorted in ascending order. All right, so we have our lowest value at the top, our highest value here at the bottom. Because this is an even number of observations, 20 is an even number, right? We break this into two perfect subsets. So subset 1 is going to be 1 to 10, and subset 2 is going to be 11 to 20. The median of the first quartile, all right, so the median is the value of subset 1 to 10. So we would type equals median A1 to A10, and that's contained in cell D2 here. All right, because it's an even number. So 1 to 10, median of 1 to 10. And this is saying get the median of all the values from 1 to 39. And then our third quartile is going to equal the median of this subset, which is value 40 to 99, and that's observation 11 to 20. So observation A11 to A20 is our third quartile. All right, so now we have our first quartile value and our third quartile value. So the interquartile range, do you remember what it is? If you said the value of the first quartile subtracted from the value of the third quartile, you're correct. So interquartile range is the value of the third quartile, which is 46.5, with the value of the first quartile, which is 32, subtracted from it. So therefore, our interquartile range is 14.5. So now we're ready to find the outlier range. So to do this, we have to take the value for the upper limit, and the value of the upper limit is going to be our third quartile value, okay, which is 46.5, and we're going to add it to the product. Make sure you put the parentheses here, okay? We're going to add it to the product of the interquartile range multiplied by 1.5. So with this, and you can do this in Excel if you like, but if you wanted to do it with pencil and paper, it is 46, okay, which is our third quartile range. Excuse me, our third quartile value. 46.5, our third quartile value, plus the product of the interquartile range, which is 14.5, multiplied by 1.5, because the upper limit is calculated by the addition of the interquartile range multiplied by 1.5 to the third quartile. So what's the lower limit? The lower limit is the first quartile, 32, and from that we're subtracting the product of the interquartile range, which is 14.5 multiplied by 1.5. So the lower limit is calculated by the subtraction interquartile range times 1.5 from the first quartile. All right. So this is real easy. It's 32 minus the product of 14.5 times 1.5. Okay. So we are now prepared to identify and remove the outliers from the sample set if we find it to be appropriate. Remember, sometimes you want to leave the outliers in there because it presents the most robust summary of the data if we're providing summary statistics and mean is amongst them. However, for the case of accuracy, in some instances, if we're assuming that outliers in this instance are not representative of the status quo assumption, we'd remove them. And remember, think of the situation where one particular semester for our course, our lecture has a couple of basketball stars in it, which drives up the median height. Or maybe we have a couple football stars, which drives the median weight one way or the other. All right. And it's not in that instance providing what we believe would be a typical representation. So we go ahead and remove those individuals. But we let our readers know that we performed these calculations and we removed X amount of outliers, or N amount of outliers for that matter, from our data. All right. And we also should report the upper and lower limits as well. So we are now prepared to remove the outlier values from our sample set. Outliers in this case are any value greater than, not greater than or equal to, greater than. So if you have a value that equals 68.25, by the methodology which we're employing, we leave it in the set. It's only values greater than 68.25. And any value less than 10.25. Remember, if it's equal to 10.25, we keep it in. It has to be less than. So 10.24, 10.23, 10, 9, 8, so on and so forth. 10.25, value equaling that, we leave it in. And that's because our upper limit is 68.25 and our lower limit is 10.25. Values equal to the limit values remain in the set. Don't get this far and then get this wrong. Because somewhere in the internet ether, I'll shed a single solitary tear. So these are the outlier values that we are going to identify from our methodology that we employed as it pertains to removing outliers or identifying outliers. So 1 and 7 are less than 10.25, so they go. And 88 and 99 are greater than 68.25, so they're identified. And if we find it to be appropriate, they're removed. So I'll show you how to do this in R. All right? You can do this in R or RStudio. But here's how you would do this in R. And there's ways that this can be also achieved in R Commander, which we'll do in a later lecture. But let's just do a quick and dirty application in R. So let me get my R open for all of you, or RStudio. Come on, RStudio. Is RStudio not going to cooperate? Loading here. Oh, here we are. All right. So if you wanted to do a calculation similar to the calculation which we've just performed in our analysis from the prior slides, you could use this code here in your RStudio interface, or you could just do it in R, whatever you prefer. But in any event, we're going to create a data set or a data vector, and we're going to have our elements within that be 1, 7, 27, 30, 31, so on and so forth. So we're going to assign these values to our outlier test. And then we're going to create a box plot. So let's go ahead and make sure these values are appropriately assigned. There they are. And now let's create a box plot. And I'll explain how all of these various concepts come together in the box plot. So this is how you would create a box plot if you didn't want to use R Commander. If you just wanted to do this in RStudio, you would first have to define your elements within a data vector, and then you'd have to use this code here, this function, to create your box plot. So here's the box plot that will be created from our code. All right, so this is the example we just did in Excel. All right, so this is that data visualized in a box plot created from R. So let me explain what's being displayed here. And in this case, again, we're keeping the outliers in. We're not removing outliers. If we wanted to remove the outliers, we'd have to, let me close this. We'd have to remove 1 and 7 and remove 88 and 99. And then reassign, well, make sure this is closed up. We then reassign the elements, and then we'd recreate our box plot. And if that were the case, this is what the box plot would look like with the outliers removed. But we're going to pretend that we keep our outliers in. And in that case, we'll be looking at what the box plot, or as we referred to it in the beginning, box and whisker plot, is illustrating. So let's get out of this. And the code will be in the video description if you wanted to follow along at home. So this is what the box plot is illustrating if we're a unbiased third party reviewing the data as it's presented to us. So if we see a box plot, the middle slash that is vertically displayed, that is the median of our data. So that would be the second quartile, or the median of our data observations. The leftmost portion of the box, that's the first quartile. And the rightmost portion of the box, that's the third quartile. All right? So median, first quartile, third quartile. What are the whiskers displaying then? Remember we called it a box and whiskers? What's going on with these whiskers? Well, the leftmost whisker, that's the lowest non-outlier observation value in our set. The lowest non-outlier observation value. And the rightmost whisker, that's the highest non-outlier observation value. So as it relates to our data over here, that would be 27 on the left. That's the lowest non-outlier observation value. And the whisker on the right would be 48. That's the highest non-outlier observation value. And our quartile values would be 31. That would be the box point on the left. And 46.5 would be the box point on the right. 46.5, that is. So this would be 46.5 over here with our various values. Now, any points that exist outside of a whisker, those are our low outlier values or high outlier values, depending on where they appear. So low outlier values would appear to the left because they're lower than the minimum non-outlier value. And high outlier values would appear on the right because they're higher than our maximum non-outlier value. So if we were to take the data which we had assessed in our Excel observation, and we were to feed it into R with the outliers contained within it and create a visualization, which we did earlier in this example exercise we've been going through, this is what that would resemble. Now you're probably thinking, well, this is all well and good, but what does this all mean again? Well, here's the box and whiskers on the left with our values on the right. Here's the median of our data set in its entirety. That's 39.5. Here is the upper quartile, or the third quartile, 46.5. Here is the first quartile, 32. Here is the lowest non-outlier value, 27, on our one whisker. And on our other whisker, we have the highest non-outlier value, 48. And then we have our outlier values as defined by the methodology which we reviewed throughout the slides. Those values being 88, 99. As you can see, they exceed the maximum non-outlier value, which is 48. And our low outliers are 1 and 7. They're smaller than our minimum non-outlier value, which is 27. So here are those outlier values over here. And the technique from which the outlier values are defined as it relates to this box and whisker plot, that technique is the technique which we discussed in the earlier slides, which was values which exceed, let's go back, values which are greater than 68.25, less than 10.25, and those were calculated by the interquartile range multiplied by 1.5 as added to the third quartile value, and the interquartile range multiplied by 1.5 as subtracted by the first quartile value. So that provides us, as it pertains to the data set, which was our example data set, with this visual here. Now, obviously, your box and whisker plots will differ depending on the data set which you're observing. However, the way in which the box and whisker plot is structured as it pertains to median, first quartile, third quartile, maximum non-outlier value, lower non-outlier value, lowest non-outlier value. All of that is going to be presented in a similar manner but you may or may not have outlier values, and your box might be thicker or smaller, thinner, depending on what data you're utilizing. But the structure will remain unchanged. Okay? So I hope that this video was useful for your research needs. I appreciate you stopping by. Like and subscribe if you enjoyed the content, and have a wonderful rest of the day. Take care.